Okay, go on, Milo.
Okay, can you hear me?
Yep.
So this presentation's on network communication devices, and it'll go through network communication devices in the way of how they are connected together to get end-to-end communications, and covers the basic operation of network infrastructures, including wired and wireless networks. So the content we'll be going through are network devices and wireless communications. Network devices. To distinguish one end device from another, each end device on a network has an address. When an end device initiates communication, it uses the address of the destination end device to figure out where to send the message. An end device is either the source or destination of a message transmitted over the network. The figure to the right shows data moving through a network. Routers. Routers are devices that operate on layer 3 or the network layer. They use the process of routing to forward data packets to other networks. The routing process uses network routing tables, protocols, and algorithms to figure out the best path for forwarding an IP packet. Routers update other routers in a network by gathering routing information about changes in the network and increase scalability of networks by segmenting broadcast domains. And the figure to the right shows how routers work, or where the routers are in the network. Routers have two main functions, which is path determination and packet forwarding. To do packet determination, each router builds and maintains a routing table, which is a database of known networks and how to reach them. The routing table can be built manually and contain static routes, or can be built using a dynamic routing protocol, so DHCP. Packet forwarding is done by
Wait,
using it.
what about DHCP did you say?
I assume the dynamic routing protocol is DHCP.
No.
All right.
So, but the previous point, I mean, the example is wrong, but your point was right. So routing protocols, they facilitate routing between internet networks. So look at go back to the previous slide, Milo. Look at the figure in front of you. So DHCP, Dynamic Host Configuration Protocol, is the protocol that automates the assignment of IPv4 addresses to end machines. Therefore, where do you expect to see the DHCP servers? Inside LANs. So inside those yellow color boxes in this figure. This is where the DHCP server is sitting and is providing IPv4 addresses to end machines. Whereas routing protocols, as the name routing or routing suggests, happens between routers. Therefore, in the box in the center, between those routers only, this is where routing protocols are operating. Different examples of routing protocols that this chapter also covers basics of them. So RIP, RIP, Routing Information Protocol. OSPF, Open Shortest Path First, Link State Routing Protocol. EIGRP, Enhanced Interior Gateway Routing Protocol. BGP, Border Gateway Protocol. Those different examples of routing protocols, they are working inside that. Which color is that? Velvet color box in the center. Yeah? Move on. You're muted.
Packet forwarding is done by using the switching function. Switching is the process used by a router to accept a packet on one interface and forward it out of another interface. One responsibility of switching is to encapsulate packets in the appropriate data link frame type for the outgoing data link.
So most common network devices that you have heard and you have learned so far are routers and switches. Switches, they operate at layer 2. Routers, they operate at layer 3. Don't confuse switching when we are talking about routers with what we mean by switching in the context of switches. So we have two different stories, yeah? Switching and routing. Both of these stories are about forwarding. Switching is layer 2 switching, and it's about forwarding frames, and it happens within switches. Routing is forwarding of IP packets. I'm not using the word frames, which is a layer 2 context. Forwarding packets. In this chapter, the textbook discusses how routers perform switching. This switching is about packet forwarding. So it's not what switches do as switching with forwarding frames. Yeah, so don't confuse this switching with the switching that switches they do in the form of frame forwarding. So yes, we're going to see how routers do switching in a sense that how routers do routing in a sense that how routers forward IP packets, layer 3 packets. And this slide, which is next slide for Milo, explains this concept very well. But just before we move on to this slide, look at the board, not your screen. Not sure how, if everyone can see it. So basically, this is, if you can't see it, just look at it and then find it on your NetAcad curriculum, the figure, bring it up in front of you. So this slide, just let me tell you which section of NetAcad we are talking about. Open up NetAcad, everyone.
I think it's 11.1.3.
Yep. So go to that section, please. I don't have it yet. Bear with me. What was it, Aaron?
11.1.3. Should be the second, like in the video thing.
Yep. So this slide tells you the routing table. Back to switches and switching. If you remember from last year, we had switching table or forwarding table on switches. Routers, they also have what we know as routing table. So show IP route shows the content of the routing table, what is inside that routing table. At the moment, for instance, you can see 3 networks being advertised to R1, or at least R1 is aware of. 2 of the entries inside routing table, which are the first 2 entries, are highlighted with the source route C. C at the beginning of those 2 stands for connected. So connected networks are the directly connected links of the router. As soon as you issue no shutdown and assign IP address to those router interfaces, those 2, so I'm talking about the need in an interface on the right hand side of R1 and an interface on the left hand side of R1. Yeah. As soon as you assign IP addresses and issue no shutdown, those 2 C entries will be added within the routing table of R1. Someone has also manually, with S for static, advertised 192.168.3.0 on R1, which, if you pay attention to, is the very remote LAN on the very right hand side of this topology. Yeah, on your NetAcad. Just message Anaida and ask for it. So those 3 are added. Yeah, so routing table therefore consists of network entries around known subnets that router is aware of. And what happens is whenever that router R1 receives an IPv4 packet, it will examine the destination IP address of that IP packet. If there is a match between that destination IP address and one of these networks that R1 is aware of, then R1 knows how to forward it. And by switching here in this context, we mean this, how to forward that IP packet. How? If the destination IP address for an incoming IPv4 packet to R1 is 192.168.3.10, for instance, R1 looks at its routing table and finds out that it falls within 192.168.3.0/24 within that subnet. It's an IP belonging to that subnet. Therefore, you see at the end, it says via 192.168.2.2. This is the next hop. This is how packets destined for that subnet should be routed, by being sent to the next hop IP of 2.2. Make sense? Move on.
Encapsulating and de-encapsulating packets. So in the figure, PC1 is configured with IPv4 address 192.168.1.10 and a MAC address of 0A10. As a packet moves from the source device to the destination device, the layer 3 IP addresses do not change. This is because the layer 3 PDU or protocol data unit does not change. The layer 2 or the data link layer addresses change at every route on the path to the destination as the packet is de-encapsulated and re-encapsulated in a new layer 2 frame.
So just follow up the orange color arrows here, and you see what we mean by encapsulation, de-encapsulation, and re-encapsulation. So from left to right and from top to bottom, from left-hand side, you see that the original message gets encapsulated as it travels down the protocol stack. As Milo said, the IP address is end-to-end addressing mechanism, and therefore source and destination IP addresses won't change all the way from left to right. At each hop, though, let's say the very first router R1 will receive that data packet and will de-encapsulate it, meaning that the layer 2 header and trailer will be stripped off the frame to expose what is inside that encapsulated frame, which is the IPv4 packet, and delivers it to the layer 3 on R1. Layer 3 now looks at the destination IP address, as I said in the previous slide, and examines that and consults against its routing table to see where to forward that IPv4 packet. Once the decision is made, R1 now needs to re-encapsulate that IPv4 packet into new layer 2 frame, which matches this link, the link between R1 and R2, because layer 2 encapsulation may change from one hop to another depending on the data link protocol that we are running. So Ethernet, for instance, is the data link layer protocol that we are running and we see most commonly. However, pay attention to the link type between R2 and R3. There is a serial cable, unlike previous links, between R2 and R3. Therefore, encapsulation for the packet into frame is different from what you see previously, because there is no Ethernet technology between R2 and R3. So what is the layer 2 data link layer protocol between R2 and R3 over that serial link? It's called point-to-point. Yeah, P2P, point-to-point protocol is running between R2 and R3, because serial cables, the data link technology over serial cables is point-to-point. And therefore, there is no Ethernet frame header in the form of destination MAC address that you see previously. We will get to that later in this chapter as well. And then you get to the very final destination and you strip off headers from bottom to top, layer by layer. This is called de-encapsulation until we get to the user on the very right-hand side. Just before I go back to question, making sure that I covered the points I wanted. Okay, go on, Aaron.
So, you know, you said that's point-to-point protocol. Isn't that just a layout, not a protocol?
No, so it's a protocol itself as well. Don't
Okay.
confuse yourself with point-to-point. You can say R1 to R2 is also point-to-point. Yeah, I'm talking about protocol.
Okay.
Between R1 and R2, the destination MAC address would be that of R2's interface on the left-hand side. There is no numbering here, so I can give you the IP. So the 192.168.2.2, whatever MAC address is associated to that link will be destination MAC address for the frame that leaves R1 towards R2. Yes?
Okay.
But later you will see that this is not going to be the same when it gets to R2 to R3, because the data link layer there is not Ethernet, it's point-to-point protocol.
Okay. I didn't know that was a protocol. Thank you.
Yep. Okay, move on, Milo.
The packet forwarding decision process.
This slide is very important. It tells you the story that I told you earlier about how routing protocols work. Yeah, Mova?
The data link frame with an encapsulated IP packet arrives on the ingress interface. The router examines the destination IP address in the packet header and consults its IP routing table. The router locates the longest matching prefix in the routing table. The router encapsulates the packet in a data link frame and forwards it out the egress interface.
So read that sentence again about longest prefix match.
The router locates the longest matching prefix in the routing table.
Yeah. So what does that mean? Anyone? So you remember earlier I said about the entries in the routing table that your destination IP address of the incoming packet will be consulted against, and then you make a decision on where to send that IPv4 packet to. What if inside the routing table I have this 10.9.8.0/24, 10.9.8.0/25. If I have one destination IP for which more than one subnet, which is at least 2 subnets, are listed inside my routing table, I'm sure you are making notes, then the longest prefix match rule applies, which means I'm going to take next hop 2 to forward that IPv4 packet through, rather than next hop 1 in this example. This is the very first rule that we have to check if for one network address, we have more than one entry inside our routing table. So this is what it means here when it says it checks and it prefers longest match rule, longest prefix match if we have more than one subnet listed in our routing table, which matches the destination IP address of the IPv4. Move on, Aaron.
Wouldn't that, so it wouldn't cause incompatibility issues at all? It would just
not at all. If you think about it, without this, you have compatibility issues.
Yeah.
You have loops. Yeah,
that makes sense.
Remember, guys, you can have summary routes. So summary routes, again, this is CCNA 1 concept. If you can't remember, go back to previous year's materials. So you can have a summary route whereby all these subnets, 10.9.8.0/24, 25, 26, 27, same thing, 27. All of these 4, for instance, will be summarized with one network. We keep using that quite a lot if we have large subnets. And then what if I have one summary route that summarizes many networks, and then I have a destination IP address which matches one of these guys over here. You see, it becomes complicated in a sense that you don't know which one to send it through with summary routes. Because with summary routes, you may have /23, for instance, here, the same thing, but /23 representing this one and this one and this one and this one. So when your destination IP address matches this, where to send it? Through this, through this, through this, or through this? Exactly to avoid confusions, we are saying that the longest prefix match rule says that the one with the more specific subnet mask will prevail. Okay, move on.
The router encapsulates the packet in a data link frame and forwards it out the egress interface. The destination could be a device connected to the network or a next hop router. If there is no matching route entry, the packet is dropped. Routing information. The routing table of a router contains...
So if one question that you can ask me is, okay, an incoming IP packet comes in, there is no matching at all between the destination IP of the packet and all those subnets within your routing table. What to do? If there is no gateway or gateway of last resort, as we call it, set on that router, and if there is no match at all, we're going to discard that packet. Move on, Aaron?
No, I was going to say similar. It would broadcast and then...
no, not at
it
all.
wouldn't.
Not at all. No. Switches, that's why I'm saying don't confuse concepts in this
Oh,
chapter
yeah, sorry.
with switching. Switches, you will see that later in this chapter as well. Switches for unknown unicast MAC address will broadcast that frame out all ports except the one on which they have received it. Because if you remember, all switch ports are part of the same broadcast domain. But routers break down broadcast domains at each interface. What do we mean by breaking down the broadcast domain? That is exactly what routers do. Routers do not forward broadcasts. There is no broadcast as such, because each router interface is a separate broadcast domain. But that wasn't the case with switches. Switches, all ports belong to the same broadcast domains. Yeah? Move on.
The routing table of a router contains directly connected routes and remote routes. Directly connected routes come from the active router interfaces. Routers add a directly connected route when an interface is configured with an IP address and is activated. Remote routes are remote networks connected to other routers. Routes to these networks can either be statically configured or dynamically learned through dynamic routing protocols.
So how do we get to know those subnets that we see inside router tables? We have either dynamic way or static way. You have seen earlier an example with the static, yeah, with the source routing listed with the letter S inside routing table, S for static, yeah? That is when you manually advertise subnets on each router. Has certain advantages and disadvantages. Whereas with dynamic routing protocols, like the ones that I named earlier, like RIP, OSPF, etc., you are going to automatically learn those subnets that we have seen inside routing tables. Another thing that dynamic routing protocols they do is that they're going to adapt to changes very quickly, because these subnets are not set in stone, in a sense that new links will join, new links will come up, existing links may go down, existing subnets may need to be revoked and needs to be removed, and therefore routing per se is a very dynamic concept, keeps changing. And dynamic routing protocols, unlike static ones, they're going to adapt to these changes. So they not only make our job as network admins easier, but also they become adaptive. Move on.
Hubs, bridges, and LAN switches. A hub acts as a multi-port repeater that receives incoming data on a port. And then
Just before you move on to hubs, if you go to 11.1.5 section, just to link this current discussion that we have with the role of ARP, Address Resolution Protocol. So this figure that we have previously seen, this one, when you think about it, you need also to include ARP, because at each hop, if you remember, we need, depending on the outgoing interface link type or network type, being point-to-point or being Ethernet, you need to find out the destination MAC address before you encapsulate that IP packet into a layer 2 frame. And for that, you need address resolution protocol. And if it's going to be IPv6 rather than IPv4, then you're going to send NS and NA messages, neighbor solicitation and neighbor advertisement, in order to find out what is the destination MAC address for a known destination IP address just before you encapsulate the whole thing into a frame and send it out. Move on.
A hub acts as a multi-port repeater that receives incoming data on a port. It then forwards this data to all other ports. Hubs use physical layer processing to forward data and do not look at the source and destination MAC address of the Ethernet frame. Hubs connect to the network into a star topology with the hub as the central connection point. All devices connected to a hub belong to the same collision domain, where only one device can send data at any given time. End devices use CSMA/CD logic or collision detection to avoid the transmission until the network is cleared of traffic.
Just before we move on, just recap from last year. What is the most stupid network element ever? Hop or repeater. As the name suggests, they just repeat signals, the incoming signals on one port out to all other ports. So they have no clue if two devices are sending signals at the same time, which results in collision. Therefore, collision may happen on hub-based networks. If collision happens, then we have solutions like CSMA/CD, carrier sense multiple access collision detection, CD, collision detection, in place to specify that the collision has happened, and therefore all those nodes that contributed into the collision are going to back off for a random period of time and then try to resend after that time. And in this way, we try to avoid collision if we can. Then after hubs, we have bridges. Yeah, a bit more intelligent, a bit, than hubs, in a sense that they have two ports, as you would imagine with a bridge, and then you're going to break down collision domain into two smaller collision domains. And then you have switches, and switches are known to have a bit more intelligence than hubs, in a sense that now you're dealing with multi-port bridges. When we are saying a switch, we are talking about a multi-port switches, and therefore they are going to highly break down the broadcast domains. In fact, each switch port becomes one single collision domain. Did I say broadcast domain? I apologize. Collision domain. So each switch port is going to break down that very large collision domain into a smaller one, and each switch port is going to become a separate collision domain. However, all these switch ports still belong to the same broadcast domain, and therefore we move on to routers as the devices with a bit more intelligence now. And then router ports not only, of course, break down the collision domains, but also break down broadcast domain. And then, of course, a bit more intelligence, if you wish, you go with firewalls. Okay, move on. Milo?
Bridges have two interfaces and are connected between hubs to split the network into multiple collision domains. Collisions are contained by the bridge to a single segment and do not affect devices on other segments. A bridge makes forwarding decisions based on Ethernet MAC addresses.
Whereas hubs had no clue about MAC addresses. Bridges, as I said, they have a bit of intelligence. And that comes also in the form of making decision based on those destination MAC addresses of those two ports on the bridge. Move on.
Switches are multi-port bridges that connect devices into a star topology. Switches segment a LAN into separate collision domains which are assigned to each port. A switch makes forwarding decisions based on Ethernet MAC addresses. Switching operation. Switches use MAC addresses to direct network communications through the switch to appropriate port and toward the destination.
This switching operation is, Aaron, what you mentioned earlier. This is forwarding frames. This happens within one single broadcast domain. And this is where you see broadcast frames being sent and received and processed. Yeah, so this is proper switching. Don't get this one confused with the switching, the word switching that you have seen previously with regards to routers and how they forward IP packets that in the context of routing, we call it switching as well. But this is a separate switching concept. Move on.
A switch is made up of integrated circuits and the software that controls the data pass through the switch. For a switch to know which port to use to transmit a frame, it must first learn which devices exist on each port. As the switch learns which ports go to which devices, it creates a CAM, or Content Addressable Memory Table. A switch builds its MAC address table by recording the MAC address of each device that is connected to each of its ports. The switch uses the information in the MAC address table to send frames to a specific device out of the port to which it is connected. VLANs.
So just for you move on to VLANs. There are a couple of slides that I need to discuss, but I do it later to basically complement what you have said. So pay attention to section 11.1.10 on your NetAcad. What we know about switching, in fact, switching on switches happens in two phases. The first phase is called learning, and the second phase is called forwarding. With learning, at the very beginning of the scenario, we're going to have an empty table. This table, similar to routing table in routers, here is called forwarding table or MAC forwarding table, or what we know as CAM, Content Addressable Memory. It's kind of table that is implemented in hardware for the table for the lookups within the table to be more speedy. As you know, as you would imagine as second-year cybersecurity undergrad students, if we can implement things in hardware, it's going to be faster, but it's going to be more costly. Whereas in software, we can have more intelligence, but usually we have less speed, and then usually we have less cost involved. Anyway, so CAM is one of those hardware-based tables that are accelerated for lookup processes that happens within it. At the very beginning of the scenario, CAM table is empty. As you start sending the very first frame, let's say in this example, PCA with the MAC address 0A, with the MAC address ending in 0A, will send the very first frame. Now the CAM table or MAC address table is going to write it down that on port 1, MAC address 0A or machine with the MAC address 0A exists or lives. And in this way, as frames are being exchanged, the CAM table is going to be populated. This is learning phase. And the second phase is forwarding. When I receive a new frame for which I have some information within this table, then I don't need to broadcast it blindly to all other ports to see who is the actual destination MAC address that I'm after. I know I have information. I just go and send it to the exact person because I know where he's sitting. What if I don't have that information? What if the CAM table does not have any entry for the destination MAC address? Then that is known as unknown unicast, because you have no clue about the destination MAC address. Unknown unicast, what is the behavior of the switch towards an unknown unicast destination MAC for an incoming Ethernet frame? The behavior is to forward it out all ports except the one on which I was receiving that frame. What is the process called? The process of sending out something all ports except the one on which I have received it. This is called, no, this is called a split horizon. Split horizon, which is of course a form of broadcast, you're right in that sense, is sending out that frame all ports except the one on which I have received it. Why do we have a split horizon? Because I don't want loops. Because imagine that you can connect two switches together, and these two switches which are connected together, they can also send frames to each other. And if I send it out all ports, including the one on which I have receiving this, then that causes loops if I have two switches connected together. And split horizon is a mechanism there to avoid loops. So that is learning and forwarding phases of switching. Now we have another concept around VLANs. Move on.
VLANs provide segmentation and organizational flexibility and provide a way to group devices within a LAN. A group of devices within a VLAN communicate as if they were connected to the same network segment. Unicast, broadcast, and multicast packets are forwarded and flooded only to end devices within a VLAN where the packets are sourced. Packets destined for devices that do not belong to the VLAN must be forwarded through a device that supports routing. VLANs create a logical broadcast domain that can go to multiple physical LAN segments and improve network performance by dividing large broadcast domains into smaller ones.
Read that sentence again.
Or the last one.
Yes, VLANs and broadcast domains. What's the relationship?
VLANs create a logical broadcast domain that can go to multiple physical LAN segments.
Each VLAN on its own is a separate broadcast domain. When you buy a switch and you unbox that switch, that brand new switch, all the ports on that switch belong to one VLAN, and that VLAN is VLAN 1, which is the default VLAN. Then later, you start creating VLANs. How? You get, I usually say this, you get a virtual saw and you cut down that physical switch into a couple of virtual switches or mini switches. Each mini switch is a VLAN, in a sense that if you remember, all ports on a switch belongs to one VLAN, belong to one broadcast domain. By the same token, each VLAN corresponds to one single and separate broadcast domain. So what happens if I want to reach one VLAN from another? It's as if you are going to reach one LAN from another LAN. And what is the device that separates LANs from each other? Router. So in order to get from one VLAN to another VLAN, a layer 3 device like a router or like a layer 3 switch, or MLS we call it, layer 3 switch, should be involved, because you are going to deal with two different broadcast domains. Once again, to recap, each broadcast domain corresponds to one network address or one surname, if you remember, when we've done IP addressing together. Yeah. So what is the advantage of having VLANs? Go to this section on NetAcad, is 1.12 on NetAcad. Look at the scenario in front of you. It's on the board as well. In one building, this business, the offices and business, is spread over 3 different floors. However, people who are sitting, some people who are sitting on the 3rd floor, they are colleagues to people who are sitting on 2nd or 1st floor, in a sense that they are both IT personnel. Yeah, like we've got Anaida here. We've got Anaida's colleagues here. Both of them, they are working with IT and digital services at the unit, but they're sitting in different floors. With VLANs, we assign some ports on the switch that you see on the third floor as part of VLAN 2, which is for IT, and some ports on the switch in the first floor will be also grouped together and called members of VLAN 2. The result is that though physically they are in different places, logically they are part of the same VLAN, i.e. they are part of the same mini switch, i.e. they are sitting next to each other logically without them being physically next to each other. Each VLAN corresponds to a separate broadcast domain. This is good from cybersecurity viewpoint as well, because you cannot snoop on other VLAN information. Previously, without VLANs, while all ports of the switch belong to the same VLAN, if any of these machines have Wireshark or any sniffing software or network analyzer software, then they can start eavesdropping on other ports on that switch within the same VLAN. Whereas when you have VLANs, when you cut down that physical switch into some smaller mini switches, virtually of course, then one mini switch cannot snoop on other mini switch because they are part of different broadcast domains. So network analyzers are unable to hear and eavesdrop. So security reasons, functionality reasons, application reason, all of these are basically reasons, and they give way to usage of VLANs within our networks. Move on, Mino.
STP. So STP, or Spanning Tree Protocol, makes sure that there is only one logical path between all destinations on a network by blocking redundant paths that can cause a loop in the network.
Just before you move on, how we jumped from VLANs to STP, we are talking about different layer 2 technologies. Yeah, STP is another layer 2 technology. What is the usage of STP? Usually, we're going to have redundant links and redundant devices to avoid single point of failure. And we have scenarios like, what if this router goes down? What if this single switch goes down? The entire network comes down. Earlier, Milo told us that a switch builds up a star topology, isn't it? So star topology, what happens if the center of the topology, which is a switch, goes down? All those, let's say 24 hosts or in machines, will lose connectivity. So for these reasons, we're going to have redundancy, and redundancy comes in the form of redundant devices and redundant links. However, I can have easily scenarios whereby I'm going to create loops within my network. STP is a layer 2 technology. Don't confuse this one with routers. You can't have that between routers. You have that between switches. So I have S1 here. I have S2 here. I have S3 here. And then I have N machines or hosts here. I'm going to create this guy and this guy together as well. Why? Because if this, without this link in between, if this switch goes down, if an attacker manages to bring down S2, all these PCs are going to lose connectivity. Whereas if I have redundancy here, if S2, if this link, for instance, goes down, this link still works, and these devices can reach the rest of the network. However, I end up with a loop. And this is not the only scenario. As I said, we're going to have duplicate links to make sure that if one link goes down, another link comes up. We're going to have duplicate switches. So in case that one switch goes down, another switch takes over. So for all those reasons, which are valid reasons, which are realistic reasons, loops can happen within your network. STP's job is to avoid and break down these loops. How? STP, just an example before, spanning tree protocol is going to calculate one active spanning tree which spans over the entire network without loop. It runs an election, and at the end of the election, some of these ports come up in the blocking mode. Like here, for instance, this one becomes blocking port. Blocking in a sense that the port does not contribute into the transfer of data, but the port still receives STP communication itself. STP communication is sent and received through exchange of messages called BPDUs, which stands for Bridge Protocol Data Unit. This blocking port still sends and receives BPDUs. So it doesn't mean that it goes dead, yeah? It's still there. It receives and sends BPDUs, but does not send or receive any user data. In that way, STP, for instance, in this example, creates this structure. Look at the board, S3, S1, and S2. Though physically they are all connected together, logically there is one tree which doesn't have any loop, and they all end up with one root of the tree. This root, by the way, is called bridge root or root bridge, which is the root of the tree. There is no loop there, logically. Physically, this link exists and there is a loop. And this is job of STP, to convert any loop-based structure of trees as such to this. Yeah? So what happens is that as soon as this, let's say we have redundant links here. As soon as one of these links go down, BPDUs will inform that this link goes down, so this blocked or port in blocking mode now comes back to forwarding mode. And not only starts transmitting BPDUs, but also user data. So it's active protocol or topology in a sense that it keeps monitoring the status of links and devices. If one goes down, another backup will come up. But again, it's a loop avoidance technology. So at the end of the day, we don't want loops within our network. SCP, you learn about it in details in CCNP, not CCNA, but CCNA CyberOps basically touches STP. What is the reason? Can anyone tell me any attack vector? So remember from LVX, we discussed about how attackers think, and we told you that they learn how a protocol works, and then they try to mess up with the order, the proper order or normal order of the protocols. So here, I told you that root bridge is S3. Yeah, and I'm not going to tell you how, but there is some values that if you set, S3 becomes root bridge, or any other switch becomes root bridge, if you want to override the STP behavior. But what is the attack here?
What are you talking about? Manually changing S3, the MAC address, because it's an election based on the.
If you can, yeah, good. If you can corrupt the result of the election, as many countries, powerful countries, they do today in the world. So if you can corrupt the result of the election, if you can enforce which switch becomes root bridge, because if you see the board, the root bridge is going to be root of that spanning tree, isn't it? So traffic needs to go through that way and reaches root. If attacker inserts new switch into the topology and forces everyone to rerun an election in the form that his switch becomes root bridge, which is very easy to do, because I told you earlier that you just set a value, and if that value is more attractive than other values, then your switch becomes root bridge. You force re-election, and you are the winner of that re-election. And then the traffic comes through you. Yeah, so SCP, so why you learn these protocols and technologies, how it is related to cybersecurity. This is just one example. Move on.
A port is considered blocked when user data is prevented from entering or leaving that port. This does not include BPDU or bridge protocol data unit frames that are used by STP to prevent loops. The physical path still exists to provide redundancy, but these paths are disabled to prevent loops from happening. If the path is ever needed for a network cable or switch failure, STP re-evaluates the paths and unblocks the required ports to allow the redundant path to become active. Multi-layer switching, the routed ports. Multi-layer switches
Yeah, move on.
Okay. Multi-layer switches or layer 3 switches forward frames based on layer 3 and 4 information and also do everything that a layer 2 switch does.
So basically, so far we kept saying that switches are layer 2, routers are layer 3. We still say that, but we have another set of networking devices which are called MLS, multi-layer switches, also known as layer 3 switches. Because as you expect, the normal behavior of a switch is to only understand layer 2 language, not layer 3. That is still true, but if it's an MLS or layer 3 switch, it can not only speak layer 2, but also layer 3. They're more expensive. Many of features of forwarding in MLS is implemented in hardware or are implemented in hardware, and that's why they are faster, they are more efficient, and of course more expensive. MLS switches, as the illustration by Milo shows here, this is the icon that you use in packet tracer or basically in any topology when you want to describe existence of layer 3 switches. You see that the redundancy between MLS is very important. You don't usually use MLS for your end user facing part of the network. You go with normal layer 2 access switches. But at the backbone of the network, at the backbone of your LAN, with core and distribution layers, which you're going to see shortly what I mean, inside your LAN architecture, towards the backbone or towards the center of the network, you're going to have MLS switches if you can afford it. And then what is important is redundancy between them because they aggregate traffic from different access switches or layer 2 switches, and they provide connectivity at the back end of your network. So, and they have more features to do with security, to do with forwarding, and more speedy forwarding, and that's why they are important. They have there are two important interface types on MLS that you should be aware of. One is called routed ports. So this is in addition to normal layer 2 interfaces or ports that any switch, regardless of layer 2 or layer 3, they have or they're capable of. So routed ports makes a layer 3 switch act exactly like a router port. So router port of a router, exactly same thing of routed port of an MLS. Yeah, so don't get confused. And then we have another interface type with MLS, which is called SVI, Switch Virtual Interface, which acts as the VLAN interface. VLAN interface again needs to be a layer 3 interface because VLANs per se correspond to one single broadcast domain. And from one broadcast domain to another broadcast domain, as I said previously, a layer 3 device should be involved. And therefore, we're going to have different subnets. And therefore, a layer 3 address is required per SVI. So switch virtual interfaces corresponds to VLAN addresses, and we're going to see, we're going to define them on MLSs as well for inter-VLAN routing. As I said earlier, between VLANs, you need a layer 3 device, and that layer 3 device being either a router or an MLS. Move on, Milo.
Multi-layer switches support routed ports and switch virtual interface or SVI interfaces. Routed ports are physical ports that act similar to an interface on a router and is not associated with a particular VLAN. As Layer 2 functionality has been removed, Layer 2 protocols do not function on a routed interface, but some protocols such as LACP or Link Aggregation Control Protocol and Ether Channel do function at Layer 3.
So probably you don't know some of these protocols. Just to give you an idea, what are the protocols? LACP and what else? Ether channel. So pay attention to this example, for instance. Between S2 and S3, you have two links. Ether channel and that protocol that you see in your curriculum, which says LACP, we call it LACP, LACP, and has also a sibling called PAGP, PAGP. So all these three words, Ether channel, LACP, PAGP, they are talking about this simple thing, about bundling these two links together. And it is shown, if you pay attention, you have that in some slides as on your Netacad as well. It is shown with this circle on top of these links. So you bundle them together, and this technology is called Ether channel. Has many advantages. The simplest one being increased bandwidth. So instead of 1 gigabit per second link on the top and 1 gigabit per second link on the at the bottom, you're going to have one Ether channel with 2 gigabit per second. Yeah, and then you can do load balancing, and then you can participate in STP better, etc., etc. So it's again a CCNP concept, but just to let you know, this is what Ether channel is about. How to link or bundle or group those redundant links to create an Ether channel. There are two protocols in place: one LACP, LACP, one PAGP, PAGP. So again, that's beyond your level. Don't worry for that. Just to let you know that this is as simple as that. Okay, move on.
An SVI is a virtual interface that is configured in a multi-layer switch. A multi-layer switch can have multiple SVIs, and an SVI can be created for any VLAN that exists on the switch. You have previously seen SVI in last year module with me, if you remember. If I have a switch and I want to remotely configure that switch, so Anaida wants to get access to one of these switches, the actual switches that are used for this LAN here, for instance, from home, not from here. Therefore, she needs an IP address to that switch. Because if you remember, switches themselves are layer 2 devices. We can assign an IP address to them only if we want to remotely manage them. And then SVI for remote management of that switch will be assigned with an IP address, and then you can do SSH from remote networks, from home to this network, to the IP address of that switch, and then start remotely managing that switch. That was one use case of SVI, or switch virtual interface, which allows you to assign an IP address to a switch, which is by nature a layer 2 device. Another use case that now you have learned is that each SVI can correspond to a VLAN. And therefore, if you want to have inter-VLAN routing, basically forwarding packets from one VLAN to another, you can assign two separate, of course, IP addresses to two different SVIs on an MLS multi-layer switch, and then you can enable inter-VLAN routing through SVIs on that layer 3 switch. Move on, Milo. An SVI is considered to be virtual because there is not a physical port dedicated to the interface and can perform the same functions for the VLAN as a router interface would, and can be configured the same way as a router interface.
Is it an advantage or is it a disadvantage for SVI being a virtual interface rather than physical interface in this context? Anyone? Is it an advantage or is it a disadvantage?
Disadvantage.
Why?
Because in this situation, I mean, because MLSs are quite expensive typically, and you can basically just stick a switch on there, and it would work just as good as, or router, sorry, and it would work just as good.
Adi?
I think it depends, but in this situation, I'm traveling towards more to the advantage. advantageous parts because, like you said, if it needs to be, if the switch needs to be accessed remotely, there wouldn't be any other option.
Your very first part of your answer, I always like it, and this is always correct and true. And this is one of the greatest things that I've heard from you. It always depends, yeah? However, in this case, it's a disadvantage. Sorry, did I say if it's advantage for SVI? I mean, to use virtual interface rather than physical. What was the question? Was it this way or that way? So whichever way. So having a virtual interface here is an advantage. Why? Physical interfaces, they go down for valid reasons. They may go down, better to say, for valid reasons. For invalid reasons as cybersecurity attacks as well. Yeah, even some stupid people coming up to your rack room and just unplugging your devices, whatever. But of course, for valid reasons. Yeah. Whereas virtual interfaces, as the name suggests, they are virtual. They're always on. They're always physically. They're not physically. They are virtually built on that machine, but they are always on. They are always responsive. Remember earlier with CCNA materials, I told you that we keep using loopback interfaces on routers quite a lot to represent the internet cloud and remote networks. Why? Loopback is a virtual interface. But because it's always on, and because we don't want to get ourselves into the complexity of physical networks going down for many good or bad, valid or invalid reasons, we said we just simulate the whole thing with one virtual interface, which is always up. I'm not going to be worried about valid reason or invalid reason for this to go down because it must be always there, must be always responsive. SVIs are virtual, good in a sense that they're always there. You're not worried about physical complexity or hardware issues that you may get, and they're going to be responsive. Quickly, Eddie?
So we know with virtual interface, they're more expensive, right, compared to physical connections. But let's say a company, for instance, they don't have the funds for that sort of technology. How will they mitigate, or how would they sort of control, depending on the budget, their physical interfaces, if that makes sense?
I didn't quite catch that, but if you're asking about MLS switches being expensive and spending time on them, as I said, they're not going to be the user-facing equipment that you see. You're going to see them at the backbone of your network. It's more towards distribution and core layer. What?
So I said, yeah, okay, so accessing an interface virtually is more expensive than it being done on site, right?
No.
No, okay, never mind. Okay.
No. Accessing an interface, which is virtually always there and on and responsive, is more economical. That's why I said it's an advantage for having that interface. Yep.
Yes, I do have a question about the SVI interfaces. So,
yeah,
if we, for example, this picture here, for example, we have two VLANs on the left, VLAN 10 and VLAN 20, and we have a router. So we're going to configure it as a router on a stick for the inter-VLAN routing. And in terms of MLS, we don't need to set up a router on a stick. Are those interfaces going to be considered trunking SVI interfaces?
Very good question, and it shows that you remember ROAS, router on a stick, scenario that we had previously in CCNA1. So with MLS, with routed ports, you cannot have sub-interfaces. That's the point. Whereas with routers and with MLS routed port, because I said earlier that routed port of MLS acts exactly as router's physical interface, you can have sub-interface. As a result, for any ROAS topology, router and stake, you must have sub-interfaces. Make sense? And therefore, with this one on the right, you can't have, because they don't support sub-interfaces. ROAS happens if you don't have this part, and instead you have one switch, and then you make this one trunk, and go with sub-interfaces, then that router will be able to route between VLANs. But good question, I like that. Okay, move on, Milo.
Moving on to the next section, wireless communications. Wireless versus wired LANs. WLANs connect clients to the network through wireless access points or an AP or wireless router instead of an Ethernet switch. WLANs connect mobile devices that are battery powered instead of plugged in LAN devices. WLANs support hosts that fight for access on the RF media frequency band. 802.11 describes collision avoidance or CSMA/CA instead of collision detection or CSMA/CD for media access to avoid collisions within the media. WLANs use a different frame format than wired Ethernet LANs and require additional information in the layer 2 header of the frame.
So remember IEEE 802, we described that as a family of protocols that describe data link layer and physical link layer specifications. It has different variations. 802.2, what was it for? We have seen that in early chapters.
Ethernet.
Which part of Ethernet? LLC or MAC? So 802.2 was for upper sub-layer of Ethernet or data link layer, which was to do with LLC. Whereas 802.3 was to do with MAC sub-layer, which is the lower sub-layer of data link layer as well as physical layer. Now, we are saying that with wireless, 802.3, therefore MAC sub-layer and what comes underneath are going to be replaced with 802.11 specification. Some new, as a result of this change, some new fields will be required in wireless encapsulation with 802.11. So it's not going to be Ethernet frame that you have previously seen. Some new fields, as I said, will be added now. New processes will be required here. You will see it later in this chapter. For a wireless client to associate what we know as association, to associate itself with an access point, and then some new architectures also comes into the place, like those access points need to be managed by what we know as WLC, wireless controller. And through that, we get to the wired network. So guess what? You are right. Wireless is not a replacement for wired networks. So those fancy phones, laptops, iPads, etc., at the end of the day, for the backbone of the network, they meet up with wired connection again. Why? Because of speed. Why? Because of security. Why? Because of huge install base of the current wired backbone part of the network. Why? Because the RF is oversaturated, radio frequency. Because as you know, all these wireless communication happens through one form of modulation of microwave frames, the wavelength, frequency, etc. And new technologies and new developments have saturated many of these channels in terms of we don't have any more capacity as such. Therefore, wireless is where you see stuff happening close to end user. But when it gets to the core of the network, then you need to merge all those communication together and pass it through wired communication. But of course, with faster fiber optics between countries or between cities, newer, more modern infrastructure. Okay, move on.
WLANs raise more privacy issues because RFs or radio frequencies can reach outside the facility.
This is an issue that we didn't have with wire. Yeah, with wireless, you can just jump into any coffee shop and start with, of course, some skills, start eavesdropping off on the RF or 802.11 based communication around you. Move on.
And then in this slide, it shows characteristics that wireless.
This is
wired
important.
LANs use.
This is important. Basically, a comparison between 802.3, which is MAC, and 802.11. So the media access, both of them are using CSMA, but one is using CSMA CA, collision avoidance, and 802.3, of course, uses collision detection that you have seen previously with legacy hub scenarios. I told you that once they detect the collision, they're going to randomly back up for a certain period of time, etc. With CA, collision avoidance, the wireless devices are going to reserve the channel, the RF channel that they are using, for a predetermined period of time, and then communicate, and then next person, and then next person. With wireless devices, believe it or not, with your laptop, iPad, etc., being connected to Wi-Fi here, you are unable to send and receive at the same time. You are unable. But because it happens so quickly, you don't notice this. So, in fact, what happens is that all these devices, wireless devices, they are operating half duplex. They can either send or receive. And therefore, we needed a mechanism for media access because we had what we know as contention here. Devices contend with each other to get access to the medium, which is the carrier, which is the RF around us. And for that, we have CSMA CA. Of course, we have interferences with Wi-Fi 802.11. We don't have that with wired communication. But one of them is prone to more security or attack vectors for cybersecurity, which is wireless, and that is due to open coverage that they have, and due to the reason that the radio frequency is in hands of everyone, including the attacker within the premises. So, okay, move on.
802.11 frame structure. 802.11 frame format is similar to the Ethernet frame format, but it contains more fields. Frame control identifies the type of wireless frame and contains subfields for protocol version, frame type, address type, power management, and security settings. Duration is used to show the remaining duration needed to receive the next frame transmission. Address 1 contains the MAC address of the receiving wireless device or AP. Address 2 contains the MAC address of the transmitting wireless device or AP.
Just pay attention to how many addresses you're going to include inside each wireless or 802.11 or Wi-Fi frame. So in Ethernet and wired, we have only destination and source MAC addresses, isn't it? At layer 2. So here you specify the MAC for AP, the access point. You specify the MAC for the sender, the MAC for the receiver, and the MAC for gateway. Move on to the next slide. Oh, for me, it's next slide. For you, it's the same one. Yeah, move on.
Address 3 sometimes contains the MAC address of the destination, such as the default gateway to which the AP is attached. Sequence control contains the information to control sequencing and fragmented frames. Address
So
4,
remember fragmentation? We used to have that at layer 3 with TCP, with OSI, and then we used to specify within IPv4 header the fragments, the offset, etc., and the sequences, etc. Here we have that with sequence control field of 802.11 frame header. And then move on, address 4.
Address 4 is usually missing because it is used only in ADHOC mode or peer-to-peer.
Very specific scenarios with wireless that we have called ad hoc networks. Yeah, with ad hoc networks, we're going to make use of that one. But also pay attention to FCS. Header and FCS, the structure is pretty much the same as what you had with Ethernet. Yeah, so we're going to check with the trailer the whole fields and the whole data within your Wi-Fi packet or sorry, Wi-Fi frame or 802.11 frame. Okay, move on.
Payload contains data for transmission, and FCS is used for layer 2 error control.
Good.
CSMA/CA. WLANs use carrier sense multiple access with collision avoidance as the method to determine how and when to send data on a network. The wireless client listens to the channel to see if it is idle. This channel is called the carrier. The client then sends an RTS or ready to send message to the AP to request dedicated access to the network. The client then receives a CTS clear to send message from the AP.
Who sends
granting
who
access to
sends
send.
CDS? Who sends CTS, Steven? Salvatore? Wake up, wake up.
Is it the AP?
IP. Oh, AP.
AP.
Access
Yeah.
point.
So, okay, good. Move on, Milo.
If a CTS message is not received, the client waits a random amount of time before restarting the process. After receiving the CTS message, it sends the data. All transmissions are acknowledged. If the client does not get acknowledgement, then the process restarts.
All the transmissions are acknowledged to pay attention to. Yeah, with wireless. Go on.
Wireless client and AP association. Wireless devices must associate with an AP or wireless router. Wireless devices complete the following three-stage process, which
remember with TCP three-way handshake, I told you this is one of the frequently used questions in interviews, etc. This is also another one with wireless, especially if the role consists of some wireless activities. So 3 stages or 3 protocols used up until a wireless client associates itself with a wireless access point. Discover, authenticate, and then associate. Each of them, of course, they have several other sub-stages and sub-steps within, but just to know it, how it works generally. Okay, move on, Milo.
Passive and active discover mode.
Just before that, go back to previous slide. Anything else you wanted to mention? That's fine. Okay, move on.
Wireless devices must discover and connect to an AP or wireless router.
So out of 3 phases or steps in the previous slide, the very first one is discovery. Discovery is for the client to associate itself, of course, discovers and then associate itself with the AP, access point. Yeah. How it happens, we have 2 different modes, active and passive. What's the difference, Milo? Go on. Milo? No, just go on through your slides.
In passive mode, the AP openly advertises its service by periodically sending broadcast beacon frames containing the SSID supported standards and security settings.
So we have a frame type, a SISIC frame type called beacon frame. AP is going to actively and periodically, so actively for beacon, for AP, yeah, but the solution is called passive in the sense that the client is sitting there waiting for someone else to come to them. So AP is going to periodically send beacon frame advertising BSSID. Basically, it's going to say, this is my wireless LAN that I have. You want to join? Like Edgeron, like Staffs Secure, or what's it called? Secure Staffs, whatever wireless that you are using here. So guest, Wi-Fi, whatever. So the BSSID and then some settings, in particular to do with the security encryption protocol and the security that this Wi-Fi is based on, and then client is going to sit there and see if he likes it or not. If he likes it, then may go back and then authenticate, and then associate itself with the AP. Whereas with the active mode, there is no periodic beacon frame being sent by the access point. It's going to be wireless client itself to go there and having that BSSID in hand trying to start discovering the access point, authenticating himself. So he is going to be active, and that's why it's called active discovery mode. Move on.
The main function of the beacon is to let wireless clients to learn which networks and APs are available in a given area, which then allows the clients to know which network and AP to use. In active mode, wireless clients must know the name of the SSID. The wireless client initiates the process by broadcasting a probe request frame on multiple channels. The probe request includes the SSID name and standard supported. APs configured with the SSID will send a probe response that contains the SSID, support standards, and security settings. AP, WAP, and WLC. All the control and management functions.
We are going to talk about a centralized architecture for wireless LANs, for the design of wireless LANs. So far, you have seen that there is a wireless client, and using either active or passive mode, they're going to associate themselves with the access point. But what happens behind the scene and beyond that access point? This is what about? Okay, go on.
All the control management functions of the APs on a network can be centralized into a wireless LAN controller. When using a WLC, the APs no longer act autonomously, but act as lightweight APs. LWAPs forward data between wireless LANs and WLCs.
So you can have APs independently or autonomously providing the beacon frame, and then wireless clients to associate themselves and register themselves onto that, and then start using that Wi-Fi, BSSID network, whatever it is. You can have this, or you can have lightweight access points, LWAPs, which are now managed by WLC wireless controller. Therefore, we're going to go from a decentralized or a distributed architecture more towards a centralized architecture, thanks to LWAP or lightweight APs and WLC or wireless controller. What happens is that now APs, they just get the wireless frames and then they send it to wireless controller. Wireless controller is the one that is going to make the management decisions. Like, yes, I want to authenticate you. You don't have the credential. You can join this wireless network. Now you need to leave this wireless network. The network is under the saturation at the moment. So all those control and management aspects, now instead of being on the shoulder of separate autonomous access points, now they are going to be centralized thanks to lightweight access points and WLC. And by the way, this is the architecture for here. And this is the architecture for many of these Wi-Fi LANs that you are seeing these days. Because, as I said, it's going to be have less complexity, it's going to be more manageable. Move on.
A benefit of centralizing the AP management functions in the WLC is easier configuration and monitoring of access points. Any questions?
Thank you very much. That was good. You jumped some slides, but that is understandable. You wanted to make it on time.
You're muted, sir. You're muted, sir. Oh yeah. Sorry.
Here's
Only 10.
Let's move on. Who has presentation next? Elvis,
Yes.
why don't you answer then?
Well, I had my headset off.
Okay, that's good. That you know this is your turn, so put your presentation on, please.
All right.
Just bear with me, please. Just go to chapter 12, Elvis.
Yep.
Thank you. I need to issue cause for concern for 2 of you at least. As I said earlier, guys, be careful not to miss sessions. Aaron, make sure you don't miss any other session.
Yeah, sorry. Yeah.
Eric is not there. Garib is not there. Lamek is not there. Phone is not there. Look, I did it here. Okay. Okay. One. Tell us about network security. So this chapter is going to tell you about network security. Network security is another part of this module. And today we are going to go through basics of network security. Let me just share this slide as well. Okay, go on.
Okay, so chapter 12 is network communications, and the first one is going to be network representation. So each network architect and administrator must be able to show what the networks will look like. So there's a diagram you can see on the screen that shows the icons and symbols they use to represent.
These are a standard representation or way of representation for different network devices you should be aware of, yeah? Okay, move on.
Yep. Okay. So diagram provides an easy way to understand how devices connect in a large network. This type of picture of a network is known as a topology diagram. Yeah. So the ability to recognize the logical representation of the physical networking components is really critical to being able to visualize the organization and operation of a network. So here's some additional, in addition to these representations, specialized terminology is used to describe how each of these devices and media connects to each other. So first one is network interface card, NIC. NIC physically connects the end device to the network. There's also physical port, which is a connector or outlet on a networking device where the media connects to an end device or another networking device. And last one is interface, which is specialized ports.
So in the context of networking here, we're going to use these two terms interchangeably, yeah? So interfaces and ports, they're referring to the same thing. Move on.
Okay. Should I finish this one now?
Yeah, go on.
All right, so interface specialized ports on a networking device that connects to individual networks. Because routers connect networks, the ports on a router are referred to as network interfaces. So next one is a topology diagram. So topology diagrams are mandatory documentation for anyone working with a network. They provide a visual map of how the network is connected. And there are two types of topology diagram, physical and logical. So the physical topology diagram illustrate the physical location of intermediary devices and cable installation as shown in the figure on the right side. You can see that the rooms in which these devices are located are labeled in this physical topology.
Yeah, this is important for you to know the difference between a logical topology and physical topology. Physical topology, as you would expect, tells you about the exact physical location of network devices. Yeah, so which room, which rack, which shelf within that rack, this particular device is installed or is located. With logical topology, however, you're going to see IP addressing, you're going to see VLANs, you're going to see the subnets corresponding to different business departments, etc., etc. So, yeah, move on.
Yeah, so as you just said, with logical topology diagrams, it's more about addressing scheme of network as shown in the figure as well. So you can see which end devices are connected to which intermediary devices and what media is being used. So it shows different IPs, the interfaces that are connected. Okay, so next up is networks of many sizes. Simple home networks let you share resources such as printers, documents, pictures, and music among a few local end devices. There's also small office and home office. Soho networks allow people to, I can hear myself. Allow people to work from home or a remote office. Many self-employed workers use these types of networks to advertise and sell products, order supplies, and communicate with customers. Another one is a business and large organizations. Use networks to provide consolidation, storage, and access to information, network service. Networks provide email, instant messaging, and collaboration among employees. Many organizations use the network's connection to the internet to provide products and services to customers. The internet is the largest network in existence. In fact, the term internet means network of networks. It is a collection of interconnected private and public networks.
Good. You can go quicker on this side.
Okay, so in small, okay, I'll just skip this one. It's not good. Next one is LANs and WANs. So network infrastructure vary greatly in terms of size of area covered, numbers of users connected, number types of services available, area of responsibility as well. The two most common types of network infrastructures are local area networks, which is LAN, and wide area networks, which is WAN. A LAN is a network infrastructure that provides access to users and end devices in a small geographical area. A LAN is typically used in department within an enterprise, a home, or small business network. A WAN is network infrastructure that provides access to other networks over a wide geographical area, which is typically owned and managed by a larger corporation or a telecommunication service provider. So on the right side, you can see this figure shows LANs connected to WAN.
Yep, move on. So there are two other network types as well. MAN, metropolitan area networks, SAN, storage area network, with the specific use cases, as the name suggests, storage area network, SAN, LANs and WANs, of course, you're aware of it. Okay, move on. This slide is very important. You have seen this previously in your CCNA, if you were with us, and it tells you about hierarchical, 3 layers hierarchical design of LAN designs for LAN architectures. This architecture is what Cisco recommends to be used within the design of any LANs when you want to design it, with core, distribution, and access layers. What they are, what they do. One.
Okay, so the 3-layer network design model. The campus-wide LAN uses a hierarchical design model to separate the network topology into modular groups or layers. Separating the design into layers allows each layer to implement specific functions, which simplifies the network design.
Raise your hand if this is new concept to you. 3 layers. No worries. So previously, what we have seen was a flat structure of the network. Now we are going to give it a hierarchical view or design rather than a flat structure. The advantage is obvious: scalability, security. So when you have more users, you just need to go through one of the leaves of this tree rather than just buying new equipment, adding new equipment. You can just go to one leaf of this tree, like a structure. So this leaf will be expanded, will be scaled. That's it. Security, redundancy. So if the whole thing from this right-hand side goes down, the left-hand side is still makes the business continue. So business continuity reasons. So many good advantages around that. Security, of course, because you now have groupings and modular layered design. And whenever you have a layered design, you have certain points where you can enforce what we know as access control. Yeah. Leon, Salvatore, I make you both late for today because this is disrespectful to the whole class, and you keep repeating this every week. And two late makes you 1 absence. So don't be late again, yeah? Leon. Clear? Salvatore. Is that clear? Don't be late. You are repeatedly late, and this is disrespectful. Yes, 10 minutes break, not 30 minutes. Well, this is 10 minutes break. If you want to eat, take it towards your lunchtime, not now. And again, that happened with you too, with Luca and others as well, but at least they came earlier. So don't let it go like that. As I said, 0 tolerance for those things from me. Are we clear on that, Leon? Salvatore? Yes, you keep saying that it's clear and you keep doing the same thing. It won't work like that. Move on.
Yeah, so you basically covered all of that. Okay, so the next.
Wait, What's the difference between core and distribution and access layers?
The core provides connectivity between distribution layers for large LAN environments.
Core is more towards the core of the network.
Yeah.
Yes, and it interconnects large separate portions of your network together. Whereas distribution is to do with aggregation of traffic from access layer switches themselves. Also pay attention to the device type, where we have used normal layer 2 access switches and where we have used MLS, multi-layer switches. So core and distribution, we use mainly MLS. Whereas with access layer, we are using access switches. Also pay attention to the placement of VoIP, voice over IP phones. They are in between of PCs and switches because they act like switches themselves. They're like 3-port switches. 1 port for voice, you don't see that because it's not a physical port. It's in fact VLAN for the voice that we are using. And then another port towards the switch, another port towards the PC itself. So the placement of switch VoIP phones within the network is important. Pay attention to where the access point, the wireless access points are installed. It's in access layer, yeah, of this 3-layer hierarchy. And then pay attention to where the border routers are. And the border routers are the closest one towards the outside wall. And then see the device type, the icon for that router. It is not just a router, it's a firewall as well. Yeah, you see the symbol for firewall routers is different from normal layer 3 routers. Because for any outgoing traffic from your LAN or incoming traffic into your LAN, that traffic needs to be checked within that border router, within that firewall. And then pay attention to either channel symbol that you can see in the core layer. You see that circle? And I earlier told you the way that we bundle multiple physical links into one logical link in order to increase efficiency and improve on the bandwidth. And also pay attention to duplicate links on each of these switches in order to make the network more, in order to have the network to have a more redundant path in case that one link goes down, the network is still operational. So multiple devices, multiple links, and how they are interconnected, and how they are separated, and how each of them is using different device type, depending on the functionality that you expect from that level. Go on.
So to continue this, each layer is designed to meet specific function, as you just said. Yeah.
So the 3-tier or 3 layers hierarchical design, the one that you have seen previously, has one disadvantage, and that disadvantage is cost. You see multiple MLS switches that you're using. And that's why we have a collapsed core architecture, whereby core and distribution layers are merged together. And then we're going to save some costs there. The important point is this: if you're talking about different branches of your business, then probably you go with collapsed core architecture. Whereas in the headquarter LAN, or where your central office is, where other branches are connected to, you go with 3-tier or 3 layers hierarchical design. So collapsed core, a very good fit for your branches or sub branches where you're dealing with smaller network sizes, and collapse and the 3-tier one or 3 layers one, a good fit for your headquarter or your central point. Okay, move on.
So next up is common security architectures. And it is firewall design that is primarily about device interfaces permitting or denying traffic based on the source, destination, and the type of traffic. Some designs are simple, as designating an outside network and inside network, which are determined by two interfaces on the firewall. So here are 3 common firewall designs, starting with first one, private and public. So as you can see in the figure, the public network is untrusted and the private network is trusted.
We are talking about 2 different security paradigms here. The first paradigm, which is a bit of historical as well, or these days we call it a bit more legacy or history really, is what you see in this slide, whereby we consider whatever is located within your LAN as trusted, and whatever which is outside of your LAN as untrusted, including, of course, the internet. This was an assumption that we had many years ago. These days, we are talking about what we know as zero trust security paradigm, which means that even inside our LAN, we don't trust anyone. We don't trust anyone. And then we define access control depending on the role of the employee. They are able to do certain things and they are forbidden to do other things. So we assume no trust for anyone, even inside our network. But previously, as I said, we used to say inside our network trusted, outside of network untrusted. And then we had a firewall. And then for any outgoing traffic or incoming traffic, we wanted to check the type of the traffic, what is inside the packet, to see if they match the firewall rules or not. If they match, then we may permit them, we may forbid them, or deny them, or drop them. With this old security paradigm, we used to say that any traffic from untrusted network, which is outside our current LAN, into our network is going to be blocked. However, the incoming traffic is allowed only if they are return traffic for requests that we had initially requested ourselves or initiated ourselves. Like HTTP is allowed back to our network only if it's HTTP response to a valid HTTP query or request that we have initiated ourselves, we have started ourselves, or other types of protocol traffic that we have. So only if the return traffic is valid traffic, meaning that we had initiated this first ourselves from the trusted network towards outside world, then we allow it. Otherwise, anything else from external to internal is going to be blocked. Move on.
Okay, so next up is a demilitarized zone.
Demilitarized zone, or DMZs, yeah?
Yeah. So this is a firewall design where there is typically one inside interface connected to the private network and one outside interface connected to the public network.
Just in the story that I just told you in the previous slide, where we had one untrusted and one trusted, and that's it. Later, businesses came to know that they have some services which are facing the customers and they are valid and they are hosted inside. Like what? Like web services for the company. They are queried every now and then by customers from external networks, yeah, from untrusted networks. Therefore, we didn't want them to have those servers inside the core of our network because it's a security risk. And therefore, we ended up with this architecture rather than the previous architecture, saying that between trusted and untrusted, I'm going to create what I know as demilitarized zone, DMZ zones. And this is the place that I'm going to place all my customer-facing services, like web services, for instance, web services, etc., within that DMZ. It's not deep down into the core of my network. It's not placed completely outside my network where it is completely untrusted. It's somewhere in between, and it's going to be protected by firewall rules as well to see which traffic is allowed to those servers within DMZ and which traffic is not. Move on.
Okay, just to clarify something, so traffic originating from the private network is inspected as it travels towards the public or DMZ network. And the traffic originating from DMZ network and traveling to the private network is usually blocked.
Good.
Yeah. Okay, so next up is zone-based policy firewalls. It uses the concept of zones to provide additional flexibility. A zone is a group of one or more interfaces that have similar functions or features. Zones help you specify where a Cisco iOS firewall rule or policy should be applied. So in the figure, you can see the security policies for LAN 1 and LAN 2. They're similar and can be grouped into zone for firewall configurations. By default, the traffic between interfaces in the same zone is not subject to any policy and passes freely. However, in
So pay attention that behind the scene, what we are talking about is also different firewall types that we have. Yeah. So previously you have seen rule-based firewalls, whereby for incoming packets, you're going to compare them or match them against some rules, saying that whether they are permitted or they are denied or not allowed, basically. Now you're talking about zone-based policy firewalls, another type of firewalls that we are going to specify some zones. As just mentioned, you have some ports being grouped together to form a zone. So even the LAN on the left-hand side and the LAN on the bottom-hand side of this figure, though physically they are in different places, physically, logically they are part of the same zones for firewalls, meaning that the same access control rules will apply. So if someone like one of these PCs from the bottom-hand side trying to reach the server on the left-hand side, they are in the same zone. So if the access control rule is yes, you can access it, then that's a yes. The firewall will allow it because they are both part of the same zone logic. However, then we have what do you call it, the untrusted zone, the one which includes the internet cloud on the right-hand side. Therefore, the traffic from that zone to internal zones will be blocked. So zone-based policy firewalls, because you can apply policies per zone, is going to give you more efficiency, more control than just rule-based firewalls. Move on.
Yeah, so this is firewall. Firewall is okay. I don't know why this is here. A firewall is a system or group of systems that enforces an access control policy between networks.
The simplest form of firewalls are access control lists. With CCNA, if you remember, routers can define and allocate some access control lists, ACLs, and apply them to the interfaces for incoming or outgoing traffic. The access control list, ACLs, have some ACEs, access control entries. So it's a table or a list of access control entries. Each entry is simply a permit or a deny statement, where you say permit IP traffic from 1.1.1.1 to 2.2.2.2, deny ICMP traffic from 2.2.2 to 1.1.1.1, something like that. Permit and deny statements as such. That's the simplest form of firewalls. But what we work with in the real world, in real scenarios these days, is much more advanced and complex than this. And this is what we're going to see in this chapter, different firewall types that we're going to have. Move on.
So security devices, continuing intrusion, prevention, and detection devices. A network architecture paradigm shift is required to defend against fast-moving and evolving attacks. This must include cost-effective detection and prevention systems, such as intrusion detection systems, short for IDS, or more scalable intrusion prevention system, which is IPS. The network architecture integrates those solutions into the entry and exit points of the network. When implementing IDS or IPS, it is important to be familiar with the types of systems available, host-based and network-based approaches, placement of the systems, and the role of the signature categories, as well as possible actions that Cisco IIS router can take when attack is detected. So here on the right side.
Yep, thank you. So I think you have combined some subtopics together, and you jump to IDS IPS. So let me go through firewalls before we move on to that. So in the table in front of you, can someone tell me what is the section in NetACAT for others? So in the table in front of you, you can see the advantages and disadvantages for firewalls. So pay attention to where it says that firewalls can degrade or can slow down your network, in a sense that you're going to have some inspection, and therefore you're going to go and check traffic, incoming traffic or outgoing traffic, and therefore you cannot send as line speeds as before as such. Go on, Aaron.
I was just going to say it's 12.2.2.
Thank you, that's good. So another disadvantage of firewalls is that sometimes it's difficult if you deal with what we know as evasion methods or evasion attacks by cybersecurity attackers. What is evasion in this context? How does an attacker do evasion? Anyone? So evasion method is that, let's say your rule says that ICMP packet traffic is not going to be allowed into your network. This is your access control list or firewall's policy or rule. What if the attacker tries to encapsulate ICMP packet within another normal packet? In other words, what if the attacker tunnels the attack traffic within a normal non-attack traffic? This is the simplest form of evasion that can happen. Is your firewall efficient enough to basically deal with evasion mechanisms that can happen? Like what? Like tunneling. Or certain attacks have certain traces in the form of patterns. Even that can be a data pattern that can happen. Can attacker encrypt the attack traffic, the malicious code, in a form that IDS or IPS, when they examine the traffic, they cannot see that pattern or those patterns, and therefore they can go away from IDS, IPS unharmed or undetected. So evasion attacks as such is one of the disadvantages of firewalls. Sometimes they can't deal with tunneling or encrypted attack traffic. Okay, move on. Oh no, you don't move on. So the very simplest form, after we've gone through firewall categories, different firewall types, is what we know as a stateless firewall. A stateless firewall is going to only check network and transport layer. This is what I told you earlier about some permit denying statements saying that from this IP to that IP, from this application with this port number to, or that application with that UDP port number, if the traffic is allowed or is not allowed. And then we may have a stateful, unlike previous one, but which was a stateless traffic. We can have a stateful traffic firewalls. Stateful firewalls, they include layer 3, 4, and 5 as well. Stateful, in a sense that you're going to have a state table whereby you write down and you track down the sessions for your communication, or communication sessions. Therefore, you're going to say this is a return traffic for something that I have generated initially myself, because I already recorded the session information inside my state table saying that this traffic was generated. It's a HTTP request generated 5 minutes ago and now 5 seconds ago, and now I'm expecting the reply HTTP response to this. So you consider network layer, transport layer, as well as session layer, because you may have a couple of browsers or browser windows being opened, and each of them is requesting something different. And then you have proxy firewalls. Proxy firewalls, they are not only checking layer 3, layer 4, and layer 5, but also they are checking the application layer itself as well. Application layer, like, is this a Facebook traffic? If it's a Facebook traffic, is it allowed or not? Is it within business hours, 9 to 5, where many companies, they block employees access to Facebook, or it's outside of the working hours for the company policy, whatever it is. So things like that, you are aware of the application context itself, and you check that one as well. And then you have what we know as NGFW, next generation firewalls. This is what we have mainly here. This is what we have these days in businesses, in the lab, etc., etc. So what they do is that they not only take care of course, layer 3 all the way through layer 7, but also sometimes they include IDS, IPSs as well. Intrusion detection systems or servers or systems, whatever, intrusion prevention systems. As the name suggests, one of them is just, detects and sends alarms whenever intrusion happens. And another one is also aware of different ways to react once the intrusion was detected. You learn in this module and this course both IDS, IPS as if they are completely separate stories. These days, whenever we are talking about them, they are basically both solutions work hand in hand, and they are working together. So any IPS systems that you are aware of, they are already IDS. They detect the intrusion, then they prevent it. They know how to react to it by doing different mechanisms that we're going to see in later chapters as well. So more about intrusion prevention and intrusion detection. So they're going to check what we know as patterns of traffic. How IDS, IPSs are going to use sensors within the network. Pay attention to the figure in front of you. Thank you for bringing it up. So yeah, where number 2 is shown. So sensor is in fact the interface on IDS, IPS device, the physical interface. So that physical interface in IDS, IPS context is called a sensor. And this sensor senses the traffic, meaning that it receives the traffic, analyze that traffic, and then let the traffic go. By sensing the traffic through sensors, what we are after is in fact patterns of malicious data or patterns of attacks. These patterns of attacks comes from historical analysis that you have done over the time on different attacks across the globe. Many companies have done it, and they came up with some attack signatures. These signatures are the recognized patterns of attacks. Sometimes, most of the time, let's say, they cannot deal with zero-day attacks. Because as the name suggests, zero-day attacks, this is the first time that an unknown becomes known. Therefore, we don't have any signature for it. However, advanced IDS, IPS solutions, they have some methods that they can predict whether this unknown incoming traffic with high likelihood is potentially a harmful traffic or not. They can predict, and there are some machine learning going on around some of these solutions as well. So for those of you who are interested in a good, interesting final year project topic, that can be one of the things that you may consider. So how machine learning helps, I'm just saying this vaguely, so this can't be exactly your topic, but how machine learning helps to improve the IDS, IPS rate of detection for malicious traffic. I'll come back to you, Aaron. Think about it in this way, that the analysis that sensors they do to come up with the signatures and basically discover if there is any signature of malicious data or attack, this analysis sometimes comes up with some false positives. It's a genuine traffic coming in, but due to using not very accurate algorithms, your IDS IPS is going to pick up and generate a false positive saying that this is potentially an attack traffic. Then later, you or someone more expert than you in SOC Center is going to investigate and see, no, this was a normal traffic, and then is going to feed back to your machine learning based system saying that in future, if you see this traffic, this is not going to be an attack traffic. Don't generate false positive alarms. And in this way, you're going to train and train and train your database of known signatures to make sure that you get a more accurate analysis over your IDS IPS operation. Adam.
Yeah, I was going to say it's very similar to antivirus applications, isn't it? Because it keeps a track of signatures and stuff.
Yes. I think he was just explaining HIPS, host-based intrusion prevention system, and HIPS and antiviruses these days, they are the same thing, operating on host-based intrusion prevention systems and also dealing with malware in the form of antiviruses, etc., etc. So one takeaway point for you is that we can have firewalls, we can have IDS IPSs in two forms, in the form of network-based solutions or host-based solutions. Which one is the best? It depends. And the proper answer to this question is that to use both as much as your budget allows you to do. We will have HIPS, host-based intrusion prevention systems on all end machines if we can afford it, as well as the NIPS, network-based intrusion prevention systems in bottlenecks of the network or in critical points of the network, what we know as vintage points of the network, where the main highways of the traffic are basically located. You can inspect traffic there much better. Okay, move on. Oh, there is also one thing here is that once you have detected the attack traffic, then the next step is to send it to Bitbucket. Bitbucket is like a bin, a garbage area, whereby you just discard the attack traffic. In reality, you may send it to some other analyzing machines or what we know as honeypots, or somewhere that you can, your experts is in your cybersecurity operations center are going to investigate that traffic further and make some sense of it in order to update the rules for their firewalls and the signature, database signature for the database of the signatures that they have for different attack types, malicious attack types. Okay, move on.
Yeah, so I don't know if you mentioned this, but IDs and IPS sensors can be in different forms.
So can we practice in reality here in Data Junction with IDS IPS? Yes. All these routers and firewalls, they have IDS IPSs built up there as well. We will have some scenarios mainly in second semester around. So on Packet Tracer, of course, you can use IDS IPS not only on routers, but also on as separate standalone devices. But the idea is this: similar to the DHCP server, similar to many servers that we have gone through so far, router itself can act as server for those services, isn't it? Router here can also act as IDS IPS, can also act as firewall, but because this is not the primary function of a router, you don't expect full set of features here if you are just relying on IDS IPS on routers. Instead, you go with standalone firewalls or IDS IPSs in reality for the networks that you manage or you design late. Okay, move on.
Yeah, so there are advantages and disadvantages to both of them. For IDS, there is no impact. Advantage of the IDS is there's no impact on network. Latency, no jitter in your network. Also, no network impact if there is a sensor failure. And there is no network impact if there is a sensor overload. Also, the disadvantage is response action cannot stop trigger packets, and correct tuning required for response actions. And is
trigger packets, the very first part of the attack traffic is called trigger packets. Yeah, move on.
And is also more vulnerable to network security evasion techniques. As for IPS, its advantage is that it stops trigger packets and can use stream normalization technique, which I guess just normalizes the flow of overall network. Would that be right?
Yep.
Yeah. Okay, so the disadvantage is sensor issues might affect network traffic, and sensor overloading impacts the network. Some impacts on network latency, jitter. Yeah. This is just more in depth, same thing. So there's types of IPS.
Host based and network based. I think we've gone through that. You can move this. Move
Yep.
on this one. Yes, that's fine. You can move on. Yep. 3 different technologies here. So this seems to you more like Cisco trying to sell themselves and their products, and you're not wrong. But just to be aware of 3 technologies, it's not just Cisco, but Cisco apparently has the best ones. One of the reasons that Cisco has the best ones is this, guys. So search for Cisco Talos, Talos, everyone, and tell me, I'm going to pick up someone to tell me in a minute what Cisco Talos does and what Cisco Talos is about. Cisco Talos, Talos. Just read what it does, what the company, well, it's under the Cisco umbrella, but what it does, Talos in particular. Raise your virtual hand once you're happy and you know what it does. Stephen, Alexei, Hamza, Sanj, Puika. Luca, what does it do?
Cisco Talos defends Cisco customers against known and emerging threats, discovers new vulnerabilities in software, and interdicts threats in the wild before they can further harm the internet at large.
Anyone else wants to add anything? It's about intelligence to cybersecurity threats as they emerge. Who is the first-hand holder of the information for different cybersecurity attacks as they emerge? Cisco Talos is one of those first-hand holders. How? How come? Because of the location of their monitoring services. They are sitting in the most critical areas of the internet, where many cybersecurity threats tend to emerge from. And then by having that first view or first hand of information, then they are in a good position to update many other companies, of course, Cisco customers who are relying on Cisco Thales. For what? For cybersecurity intelligence. To do what? To update their IDS IPS signature, to update their firewall rules, not in the form of access control list, I'm talking about next generation firewall, into the latest. Yes? So that's why sometimes we need to learn these technologies, though it might seem to you that, okay, this is Cisco's product, but yes, but because they have like the de facto manufacturer, they are de facto manufacturer across the globe, we need for now to rely on the solutions anyway, or at least learn their solution anyway. Now, back to here. We are talking about 3 technologies that Cisco has designed to deal with 3 different categories of attacks. One being web-related attacks, one being email-related attacks, one being was it the AMP malware related attacks. So let's start with AMP. Move on.
So AMP is Cisco Advanced Malware Protection, is an enterprise class advanced malware analysis and protection solution. It provides comprehensive malware protection for organization before, during, and after an attack. Before an attack, AMP strengthens defenses and protects against known and emergent threats. And during an attack, AMP identifies and blocks policy-violating file types, exploit attempts, and malicious files from infiltrating the network. After an attack or after a file is initially inspected, AMP goes beyond point-in-time detection capabilities and continuously monitors and analyzes all the file activity and traffic, regardless of disposition, searching for any indications of malicious behavior. If a file with an unknown or previously deemed good disposition starts behaving badly, AMP will detect it and instantly alert security teams with an indication of compromise.
Good. Next one.
So it then provides visibility into where the malware originated, what systems were affected, and what the malware is doing. Yeah, so that's it for AMP.
So just read the very last 2 sentences.
Oh, the last one. Okay, AMP accesses the collective security intelligence of the Cisco Thales Security Intelligence and Research Group. Thales detects and correlates threats in real time using the largest threat detection network in the world.
This is how Thales is related to AMP, web security, and email security appliances by Cisco. Okay, go on.
So next up is WSA. Stands for Web Security Appliance. Is a secure web gateway that combines leading protection to help organizations address the growing challenges of securing and controlling web traffic. Basically protects the network by automatically blocking risky sites and testing some unknown sites before allowing users to access them.
That's good. Move on. That's fine. I think we have discussed this enough.
Okay.
So move to the next topic.
Next one is ESA.
Now move up to the next one. So email
next
security
one.
appliance. You're going to go through it yourself. There's
ACL
nothing
is
important.
not good. Okay.
Again, we've gone through access control list, and that's fine. Go to SNMP. Yeah. Move on.
SNMP. Yeah, this one?
Yeah, yeah.
Okay, so Simple Network Management Protocol. It allows administrators to manage end devices such as servers, workstations, routers, switches, and all those devices. It enables network administrators to monitor and manage network performance.
Why do you need to learn SNMP? We are talking about network security, how it is related. Sometimes we want to monitor different devices within your network from one place, which is your administrative machine, whatever, or your network security engineer, whatever. So That happens through a protocol known as SNMP. SNMP communication is going to happen through exchange of some messages like get and set and then trap. You're going to have some managed devices, and these managed devices can be any end machine or can be any intermediary machine like switch, routers, firewalls, etc. And then what is beautiful with SNMP is that you're going to set certain thresholds for your managed devices. And you're going to say, you know what, as soon as you have reached this threshold, send me a trap. Tell me that you have reached this threshold. And you can think of threshold in this context as anything, like with brute force, for instance. If an attacker tries to log in unsuccessfully, let's say, 5 times, then you're going to set a trap and say, you know what, if someone tried to log in with you with wrong password more than 5 times, as soon as they reach 5, let me know. Yeah, so we're going to monitor system in that way through SNMP. Move on, next slide. NetFlow.
Yep.
What is NetFlow?
NetFlow is a Cisco AES technology that provides statistics on packets flowing through a Cisco router or multi-layer switch.
So what we expect from NetFlow is to provide statistics. And this is statistics that they provide. And by the way, NetFlow is the de facto or the best solution out there in reality for this purpose. Provides the statistics on different aspects of your network. This is good for security and is also good for network planning, because I keep saying that you need to monitor historical data and to make some sense of it. To make some sense of it in the sense that you update your firewall rules, you update your network scalability strategy, etc., etc. How do we monitor those historical data? How do we analyze what happens through or over the time in our network? How things are changing? Remember, guys, at the end of the day, networks have very, very dynamic nature. Not only in terms of cybersecurity, that someday may randomly some attacks happen, but also in terms of planning. Because like this area, for instance, for the network in the last 3 years have been through 2 or 3 different restructure. Because business needs, they change. And therefore, your network design and security policies, etc., should change as well. So with NetFlow, you can monitor data over the time, and you can start making some sense of it. And of course, with your security, you can perform certain analysis there. Move on. You're going to see NetFlow in the labs as well. Move on.
Yep.
Port monitoring.
Yep.
This is a layer 2 security solution, layer 2. So it's called SPAN, S-P-A-N, port monitoring technology for security.
So it's
So basically,
port mirroring.
yes, and the technology is called SPAN, S-P-A-N. So what happens is that you're going to assign a machine like the one I think on the right-hand side of this slide as the machine that your analyzer or your cybersecurity engineer is sitting at. And then what you want them to do is you tell the switch that whatever traffic that you sense on this port, let's say the port on the left-hand side is faster than a 01. Whatever traffic that you send on sense on fast0/1, mirror it or make a copy of it and send it to the packet analyzer machine. This is a SPAN technology, and it's a layer 2 solution for monitoring your incoming traffic and send it to your analyzer machine for further investigation. Move on.
Syslog servers.
What is Syslog?
Syslog is basically a log of different system messages. This message is
System messages.
Yeah.
Syslog is another protocol that we use in network security, and not only in network security, but also in other use cases. But here our focus is network security, in order to gather information to do with system messages, place them in one repository, and start making sense of the stored information. for our planning, for our security, etc., etc. So the simplest form of logs in Cisco iOS devices, if you remember with the labs last year, or even with this 12 chapters that we've gone through, you're going to go and issue debug command on Cisco iOS, yeah? Under privilege exec mode, you issue debug command. You see many logs will be generated as traffic is received or is trying to be encapsulated and sent outside. Those logs can be addressed to syslog server. So not only on your machine, not only on your console, but also a copy will be sent to the syslog server. And syslog server, or what you know as collector, is going to collect all those different logs, and then later you're going to analyze. Move on.
Next up is NTP.
NTP is very important because timing is important in our network. I think I've gone through this during the beginning of this course with you, telling you how important timing is with regards to cybersecurity and also to do with the defense. So NTP is a hierarchical structure. It's a hierarchical protocol, and it comes in the form of client server as well. So NTP clients are end machines who wish to synchronize their timing with some authoritative timing sources. When I say it's a hierarchical, each layer of the hierarchy is given a number and it's called stratum. So stratum 0 is the closest one, or is in fact itself the authoritative time sources. Like BBC, for instance, they have a specific server that acts as a stratum 0, and everyone else is going to synchronize their timing with that server. So stratum 0 is going to feed timing information, valid timing information, to stratum 1, and then stratum 1 in turn to stratum 2, and the stratum 2 is to stratum 3, and lower. Remember, stratum 2 and lower are in fact the businesses, and the businesses' machines or NTP clients who wish to synchronize themselves to these timings to stratum 1 and stratum 0 servers. Move on, next slide.
The AAA servers.
So, yeah, we have another service in network security in this chapter that we should be aware of is authentication, authorization, and accounting, AAA servers. The name suggests what it does, but what is important you learn in this chapter in particular are two protocols that are used in order to implement AAA services. One is called TACACS Plus, another one is called Radius. The similarities and differences is important. So TACACS Plus is the Cisco proprietary protocol, whereas Radius is the open standard. TACACS Plus is based on TCP ports, whereas Radius is based on UDP ports. TACACS Plus is going to separate authentication from authorization from accounting, whereas authentication and authorization are going to be joined in Radius, and they just separate the accounting in Radius. With TACACS Plus, any communication is going to be encrypted, which is a good thing with regards to security, whereas with Radius, only passwords are encrypted. However, on the downside, TACACS Plus is limited when it comes to accountability, whereas you can have extensive billing with Radius that you don't have with TACACS Plus. Move on.
Next up is VPN. And it is a private network that is created over a public network, usually the internet, shown in the figure on the left.
And then what is the idea?
So a VPN is a communication environment in which access is strictly controlled to permit peer connections within a defined community of interest. Confidentiality is achieved by encrypting the traffic within the VPN. And today, a secure implementation of VPN with encryption is what generally equated with the concept of virtual private networking.
Mm-hmm.
The way it works, VPN connects two endpoints, such as remote office to central office, over a public network to form a logical connection. The logical connection can be made at either layer 2 or layer 3. So the common examples of layer 3 VPNs are GRE, multi-protocol label switching, and IPsec. Layer 3
IPsec and GRE, yeah? You learn more about them in network security part of the course and also in CCNP with GRE. Move on.
Layer 3 VPNs can be point-to-point site connections, such
Mhm.
as GRE and IPsec, or they can establish any-to-any connectivity to many sites using MPLs.
Good. So point-to-point versus any connect, MPLS basically versus IPsec and GRE. Go on.
IPsec is a suite of protocols developed with the backing of the IETF.
Yeah,
So
it's a suite. It's a suite of protocols. So you hear about IPsec quite a lot. IPsec itself does not bind himself to any specific protocol. Instead, IPsec describes the framework rather than a specific algorithm. IPsec says that for confidentiality, I may have 5 algorithms, and I can use any of these 5. For integrity, I may have 3 algorithms, and I'm able to use any of these 3. Then for authentication, I am able to use any of these, let's say, challenge response algorithms. And then you, as the user, you define what we know as IPsec policy or IPsec profile. And you are saying that, you know what, out of those 5 encryption algorithm, I want to choose this. Out of those 3 integrity algorithm, I want to choose this. And then for authentication, I'm going to choose this. So all these 3 combination, all these 3 choices or selection that you make together becomes one instance of an IPsec profile, with which the other end of your VPN tunnel must agree and can disagree, of course, but must agree, and then you can start communicating with each other. So IPsec itself, once again, is not bound to any specific algorithm for encryption, for integrity. It's more like a building blocks, or it's more like a framework inside which you can tune depending on your business needs to secure. Move on.
That's the last slide.
Any question? So